welcome to today's lecture, Math 1B, Chapter 6. We're going to continue Chapter 6. We're done with 6.1. We learned how to find the area between two functions. And now we're going to start 6.2. We're going to talk about volume. So let us review a little bit. In 6.1, we learned how to find the area between two functions. The area is equal to the absolute value. Remember that when you're talking about area, the area must be positive. We don't have negative area. In general, we can use absolute value to make sure you have a positive answer. Is the integral a to b f of x minus g of x dx. And remember that, for example, you have a region sandwiched between two functions, f of x and g of x. So suppose this is your f of x, and this is your g of x, and this is the region bounded between these two functions. This is the area of this region. So after finding the area, we're interested in finding the volume. 6.2, page 1, volume. Very well. So assume that you have a three-dimensional object. Suppose this is your three-dimensional object, and you have something like this object in three-dimensional space. You're interested in finding the volume of this three-dimensional object. So what are we going to do? We're going to cut this 3D object, slice this, and by doing the slicing, we get a little part of this three-dimensional object. Very well. You already know how to find the area of that slice. If the thickness of this slice is denoted by delta x, so this is the thickness, which is delta x. If you take this thickness and multiply it by the area, you get the volume of this slice of this three-dimensional object. If you continue the process, cutting the rest of this three-dimensional object, finding the volume of little pieces here and adding them all, we can actually find the volume of the whole shape. So this is the whole idea behind finding the volume using these little areas. So add them on, and you get your volume. So volume can be defined as the integral of the area dx. Delta x, when you take the limit of delta x, these little thicknesses are getting very small, it's denoted by dx. Remember that delta x was b minus a divided by n. When n goes to infinity, your delta x is dx. The limit of b minus a over n, while n goes to infinity. Let us go over some examples to feel comfortable about this new formula. We are still on page 1. Example. This example says, okay, find the volume. Find the volume of a solid obtained by rotating function y equals to square root of x about x-axis, and x is between 0 to 1. Graph this quite quickly, see what's going on. This is the graph of square root of x. Y equals to square root of x. You know that here you have the square root function, square root. So the graph behaves like this. And since x ranges between 0 to 1, we stop at 1. Then we're going to rotate this graph, rotate square root of x with respect to x-axis. So what I'm going to do, I'm going to take this graph and start rotating this about x-axis. So it's going to be like this. This guy, then the rotation, 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 and rotation. I'm going to continue this process until I get a three-dimensional object. By rotating my graph about x-axis, I'm getting a three-dimensional object. This is it. Square root of x. I take this and start rotating this around x-axis, and I'm forming a new three-dimensional object. So I took square root of x and rotate that around x-axis. If I rotate this around the y-axis, I'm going to get a different shape. So rotation about x-axis, rotation about y-axis is a different story. Now, what is the volume of this new object? So we know that the volume is equal to the integral of area times dx. X ranges between a to b. But what is the area? How do we find the area here? To find the area, we slice this three-dimensional object this way. Okay, perfect. If I slice this by using just a plane, the intersection between the plane and this object is going to be a circle. As you can see, it is just a circle. We have a circle. So you all know that the area of a circle, the area of any circle is pi radius squared. If you have your radius, you can easily find the area of your circle. So, what is the radius of this circle? The radius of this circle is square root of x. Square root of x is the radius of this random circle. Square root of x. So for this circle, you have pi times square root of x raised to the second power. So the area is equal to pi times x. So we found the area. We just plug that in and start taking the integral. So volume is equal to the integral. I know that x ranges between 0 and 1, so a and b are given here. 0 to 1 area, which is pi times x dx. Pi is just a constant. It is just a number. So write pi in front of your integral 0 to 1 x dx. We all know that how to find the integral of x. The integral of x to any exponent is equal to x n plus 1 over n plus 1 plus constant of integration. Here, since we have a definite integral, we don't need the constant of integration. It is equal to pi x squared divided by 2, and x ranges between 0 to 1. Don't worry about 0. Why is that? You have x here. If you plug in 0, the outcome is 0. Just plug in 1, you get pi 1 squared divided by 2, or pi over x. We are moving on to page 2. Another example for you. Okay. Question says, find the volume of the solid obtained by rotating the region bounded by, bounded by y equals to x cubed. X is equal to 0 and y equals to 8. About y-axis. Okay. About y-axis. Let me graph this for you. So when it comes to area, when it comes to volume, quickly graph them. Don't forget to use decimals or GeoGebra to make sure you have a correct graph. So let's graph it first. And note that in previous example, we had rotation about x-axis. Here we have rotation about y-axis. Let's graph these. Very well. Y equals to x cubed. We all know that y equals to x cubed has a graph like this. Then y is equal to 8. Y is equal to 8. It means that I have a horizontal line. Y equals to 8. And at the same time, it says it ranges from below by 0. So your x is equal to 0. X equal to 0 is y-axis. So let me just graph this for you. This is x equal to this. Very well. So the area is between this. This is the region. This is the little area that we have. What are we going to do? We're going to rotate this guy about y-axis. So let's rotate this. So we don't need this part. We can erase it. You're taking this guy here. And you start rotating this around y-axis. This is your graph. It's like this. Took this and start rotating this guy, and I continue the rotation. So you have a three-dimensional object, and your goal is to find the volume. What is the volume? There you go. Okay. So now you are slicing this guy the way that you can find the area. Note that I have a horizontal slicing. This is my little random area that I have here. Okay, perfect. So to find the volume is equal to the integral a to b area dx if you're rotating this about x-axis. Now I expect you to ask, hey professor, I'm rotating this guy with respect to y-axis. Do I see any change in the volume formula? I'm happy you asked that. Since we are rotating this region with respect to y-axis, the volume is equal to the integral c to d of the area dy. So this is your y-axis. Compare these two. Rotation with respect to x-axis, this way, and rotation with respect to y-axis, this way. With respect to x-axis, dx, so you can remember it this way. With respect to x-axis, horizontal axis, dx. With respect to y-axis, vertical axis, dy. Since we are rotating this guy with respect to y-axis, we're going to use the second formula. Very well. So our volume is equal to the integral. We need to find c, we need to find d. What is c? What is d? and the area dy. So note that you are taking the integral with respect to y. Your area must be a function in y. So since, note that, since we take the integral with respect to y, so area must be a function of y. Okay, let's begin. Here you have your circle, the area of your circle, this little area here. This is a circle. An area of a circle is pi radius squared. So the radius of this function depends on y equals to x cubed. So area is equal to pi, your radius, x cubed squared. If you are rotating this about x-axis, note that your area must be in y. So instead of using y equals to x cubed, x, if you rewrite this side, x is equal to the third root of y. So instead of using this, your area that you're going to use for this example with respect to y is pi, the third root of y squared. This is your area. So my volume is equal to the integral of my area pi, the third root of y squared dy, and my y ranges between 0 to 8. 0 to 8. Y starts from 0 and stops at 8. Okay, the rest is just taking the integral that we learned before. This is equal to pi. Here you have y raised to 2/3. So this is 0 to 8. Pi y to 2/3 dy. So you get y raised to 2/3 plus 1 divided by 2/3 plus 1, and y ranges between 0 to 8. You get pi y raised to, if you take common denominator between these two, you get 5/3 divided by 5/3, and your y ranges between 0 to 8. So here we have 3 pi over 5, and we plug in 8. We're not worried about 0, because 0 makes the term 0, and we're not worried about it. And you have 8 raised to 5/3. 8 is 2 to the 3rd power. You can cancel out 3 and 3. You get 2 raised to 5, which is 32. You get 3 pi over 5 times 32, which is equal to 96 pi over 5. 96 pi over 5. Let me see. I need more space. This is equal to pi 8 to 5/3 times 3 pi over 5, which is equal to 96 pi over 5. Another example for you. Still on page 2. So this example says the region R enclosed by the region R is enclosed by y equals to x and y equals to x squared, then it is rotated about x-axis. Okay, x-axis. Our goal is to find the volume. Let's quickly graph this slide and see what's going on. This is another interesting case. So, okay, x, okay, and x squared. So y equals to x is just a line, y equals to x. Then you have y equals to x squared, which is a quadratic parabola function. So let's take a look at this. This is y equals to x. So we're taking this little area, So guys, we are taking this area. It's not just one function. In previous examples, we had just one function and we rotate that curve, we rotate that function around x-axis and y-axis. Here you have two functions, two. So we're taking this little piece, this little area here, this little region here, and start rotating this guy around x-axis. So it's going to be like this. And if you just connect these together, you have your three-dimensional object, which is y rotation. And note that there is a hole in between. So if you want to visualize it better, it's going to be like this. With rotation, and here you get something with a hole in it. We learned that the volume, when we rotate a region around x-axis, about x-axis, is equal to the integral a to b of area dx with respect to variable x dx. Our goal is to find this little area after slicing. How do we find this area? It seems like I have a circle, but it's not a solid circle. It is not a solid circle. As you can see, this circle is bounded between two functions. Two functions. It has inner radius and it has outer radius. You have two radiuses and you're finding this area between these two circles. Not a solid circle. This area is bounded between two functions. The inside function is x squared, so the inside function is x squared, and the outside function, outside radius, is x. There you go. So the area is equal to pi r squared x squared minus pi x squared raised to the second power. This is your first radius, outer radius, and this is your inside radius, r. Pi r squared minus pi r squared. This is your area. So your area can be simplified into pi x squared minus pi x to the 4. Okay, now that I have my area, I can take the integral and find the volume. Volume is the integral, and my x is between 0 and 1, because if I set x equals to x squared minus x is equal to 0, x minus 1 equal to 0, x is 0, x is 1. So 0 to 1 of area, which is pi x squared minus pi x to the 4 dx. So the first one is pi x to the 3rd divided by 3 minus pi x to the 5th divided by 5. X ranges between 0 to 1. Don't worry about 0, you have x and x here. Just plug in 1, you get pi times a 3rd minus pi times a 5th. Take common denominator between these two, you get 2 pi over 50. So different books refer to this method as washer method because the slice, it looks like a washer. So you have an inner radius, you have an outer radius, then you find the area, and then you find the volume. So let us move on to next example on page 3. Example. So this example says, find the volume of the region. Find the volume of the region bounded between y equals to x squared and y equals to x about line y equals to 2. Okay, so let us graph this line.